Welcome to the Air-Independent Propulsion for Submarines presentation. This presentation was originally given to the Seattle USSVI base in October 2009. Over the last 10 to 15 years, a lot of interest has mounted in air-independent propulsion for enhancing the performance of submarines. This presentation will cover a brief history of air-independent propulsion systems and the systems that are currently in use and development around the world. To start off, we need to define what air-independent propulsion is so we have a common reference when talking about these systems. Air-independent propulsion refers to technologies which allow a submarine to operate without the need to surface or use a snorkel to access atmospheric oxygen. The term usually excludes nuclear power, even though nuclear power is by definition air-independent propulsion. Most of the air-independent propulsion systems covered in this presentation are used to charge the batteries of a submarine rather than directly for propulsion. So why has air-independent propulsion become such a hot topic around the world? Many nations look at air-independent propulsion as a way to increase the range for their submarines, improve underwater endurance while avoiding the high costs involved with nuclear power, and retaining the advantages of conventional diesel-electric submarines. The best diesel boats in the world, such as the German-designed Type 209 or the Russian Kilo, shown here, can typically remain submerged on battery at slow speeds for periods around 3 to 5 days. The air-independent propulsion systems currently in operation or development can increase that slow speed endurance to as much as 3 weeks to a month. While this is still dwarfed by the potential of nuclear power, air-independent propulsion offers diesel submarines a remarkable increase in their capability. We'll now talk a little bit about the early history of air-independent propulsion. Submarine pioneers were eager to find a way to free their boats of the necessity of having to surface frequently for access to atmospheric oxygen that their gasoline and diesel engines used to charge batteries. A number of different approaches were tried, such as chemical engines, where chemical compounds like manganese dioxide and potassium chlorate were used to heat water for a steam engine. That steam engine would then charge the batteries or provide propulsion. Other options were compressed air for the gasoline and diesel engines, but none of these systems were particularly successful. Eventually, the standard submarine propulsion plant became open-cycle diesel engines with lead-acid batteries and electric motors for submerged propulsion. It wasn't until the early 1930s when German engineer Helmuth Walter proposed a new radical submarine propulsion plant design. Walter began experimenting with propulsion using high-purity or high-test hydrogen peroxide as the oxidant. In Walter's system, the hydrogen peroxide from an onboard supply was decomposed using a permanganate catalyst to yield high-temperature steam and oxygen. This mixture was moved into a reaction chamber where diesel fuel was injected. The diesel fuel combusted with the oxygen to yield a mixture of steam and hot gases that drove a high-speed turbine. The exhaust was then condensed and expelled overboard. Walter's primary design goal was high underwater speed rather than long submerged endurance. His first prototype submarine, the experimental V-80, reached 28.1 knots during submerged trials in 1940. At this time, most conventional submarines were limited to 10 knots or less. The V-80 was about 70 feet long and served as an early test bed for studying the dynamics and control of high-speed underwater vehicles. Walter's experiments led the Kriegsmarine, the German Navy, to order 3 classes of submarines that used his engine. There was a coastal submarine, the 350-ton Type 17, and 2 ocean-going submarines, a 1,600-ton Type 18 and an 800-ton Type 26. Several other designs were looked at, but never got off the drawing board. The plans to build the larger ocean-going submarines, the Type 18 and 26, were stopped by the realization that Germany's industrial capacity was insufficient to provide all the materials needed for the boats. However, the Type 18 was modified into the highly successful Type 21 electro boat, where larger batteries provided the additional power for submerged speed operations, and the adoption of a snorkel yielded a potent combination that strongly influenced post-war design of conventional submarines. Late in the war, the Kriegsmarine did complete 7 Type 17 coastal boats, but none of these saw combat. These Type 17s displaced 300 tons and were powered by 2 2,500 horsepower turbines, in addition to their conventional diesel-electric power plant. This table shows a comparison of the Type 7C U-boat, the workhorse of the German fleet during World War II, the Type 17 and 18 Walter designs, and the Type 21 Electra boat. As you can see from the potential maximum speeds of the Walter submarines while on the Walter turbine, WT, Allied anti-submarine forces would have had a difficult time catching and stopping these submarines if they had been deployed in any numbers. While the Walter engine showed a lot of potential for high-speed submarine operations, there were problems with it too. The Walter engine submarines had a short range compared to conventional U-boats and a much higher fuel consumption rate. By the time the designs were ready for production, Germany did not have the industrial capacity to make high-test peroxide in the quantity needed for the U-boat operations. Finally, high-test peroxide is very volatile and hard to work with. It requires special piping and handling procedures and is hard to store. All of these items work together to make the Walter engine design impractical for deployment during World War II. But that did not stop people from looking into it after the war. For the British, they took one of the Type 17s, the U-1407, as a war prize and commissioned it into the Royal Navy as HMS Meteorite. Meteorite was not popular with its crew, who regarded it as a dangerous and volatile piece of machinery. Control was difficult due to the aircraft-type controls that were used for the submarine and the lack of forward hydroplanes. She was officially described as 75% safe and had a range of 123 nautical miles at 25 knots submerged. In the early 1950s, the Royal Navy built the experimental high-test peroxide submarines HMS Explorer and HMS Excalibur. These submarines were primarily built for speed trials and were unarmed, but both were fitted with the latest in underwater technology, including one-man escape chambers, up-to-date escape breathing apparatus, a streamlined hull, and retractable fittings. There were some problems with the initial designs of these submarines, but they turned out to be very fast, achieving submerged speeds of 25 knots. Because of their hydrogen peroxide fuel, submarines were also known as the blonde submarines. This class went on to prove to the Royal Navy that high-test peroxide was impractical as an air-independent propulsion system for submarines. The volatile peroxide was carried in special bags outside of the inner pressure hull, and were prone to exploding unexpectedly. Additionally, the engine room, which was not manned while underway, would often be the scene of flames that appeared at the top of the combustion chambers, and on at least one occasion, the crew was forced to evacuate the pressure hull and stand on the upper casing to avoid the fumes that had filled the boat. The peroxide fuel also was troublesome to the British, and the boats quickly earned the nicknames HMS Exploder and HMS Excruciator. The program was dropped when practical submarine nuclear power was developed by the United States. The Soviet Navy also explored various air-independent propulsion systems for submarines after World War II. They started with the Project 617, NATO codename Whale. The Project 617 was a development using the Walter turbine. There was only one of these submarines built in the early 50s, and it was commissioned in 1956 after normal sea trials. This submarine became the fastest Soviet submarine of that time, reaching 22 knots submerged, but it was never completely reliable. In 1959, before a planned refit, the submarine was out doing turbine experiments when there was an explosion while it was at a depth of 250 feet. submarine was able to surface and return to base, but after the explosion, the submarine was decommissioned and scrapped, ending the Soviet experiments with the Walter turbine. The Soviets also experimented with closed-cycle diesel engines. The Project 615, NATO codename Quebec, was a class of 30 submarines built between 1952 and 1957, with the last one being decommissioned in the 1970s. The Quebec class was fitted with 2 standard diesel engines and a third closed-cycle diesel engine. The closed-cycle diesel engine used liquid oxygen to provide the air-independent propulsion while the submarine was submerged. As you can see in the picture, the Quebec class had a streamlined conning tower with a fixed snorkel housing at the aft end of the tower. They were armed with 4 bow torpedo tubes, and early versions of the boats had twin 25mm anti-aircraft guns faired into the forward end of the conning tower, making it one of the last class of submarines to be constructed with deck guns. However, the Quebec class was plagued with problems caused by its liquid oxygen fuel. Their endurance was often limited to just 14 days due to the evaporation of the liquid oxygen, and the propulsion system led to several serious accidents. In 1957, 2 submarines were lost due to accidents caused by the oxygen system. Other incidents caused oxygen-fueled flames to burst out from all the boats. This led to the crew nicknaming the boats lighters or Zippos after the well-known cigarette lighter. The class was not considered successful because of its limited range and limited speed. It could only make 16 knots while submerged. The project was abandoned with the development of submarine nuclear reactors. The U.S. Navy also experimented with various forms of air-independent propulsion after World War II. Their experiments started with salvaged Walter turbine engines from Type 17 and Type 26 class submarines. Additionally, the Navy built their own Walter engines and experimented with closed-cycle diesels. Eventually, the unacceptable growth in the required size and weight of the corresponding engineering plants, plus the growing prospect of submarine nuclear propulsion, brought these efforts to a halt. In the mid-1950s, though, the Navy did build one more peroxide-powered submarine. It was the midget submarine X-1. X-1 was intended to test submarines for shallow water commando operations. It was powered by a modified diesel engine with a small battery-powered electric motor as backup. When on the surface, the X-1 used normal atmospheric oxygen for the diesel engine, but underwater, oxygen was derived from a catalytic decomposition of hydrogen peroxide, similar to the Walter designs. The X-1 had 400 gallons of peroxide stored in the forward portion of the submarine in a flexible bag. In May 1957, an explosion in the hydrogen peroxide storage system blew the bow section of the X-1 off. Although no one was injured, X-1's closed-cycle capability was never replaced. Her former officer in charge wrote, "The most important lesson learned from this experimental program was that high concentration, unstabilized hydrogen peroxide has no place on a fighting ship." The X-1 remained in test service until 1973 and is currently on display at the Submarine Force Museum. We'll now look at some of the efforts that are currently being developed or used by various countries for air-independent propulsion for submarines. Basically, there are 4 different types of air-independent propulsion systems. There's closed-cycle diesel engines, there are closed-cycle steam turbines, the Stirling engine, and fuel cells. We're going to discuss each of these systems next. First, we'll look at closed-cycle diesel engine systems, also known as Kreislauf systems. Typically, a closed-cycle diesel engine system uses the standard diesel engine operated in conventional mode while on the surface or at snorkel depth. Underwater, it runs on an artificial atmosphere of stored oxygen and an inert gas, usually argon. The required oxygen is usually stored in liquid form in cryogenic tanks. The engine exhaust is cooled and scrubbed and separated out, with the argon being recycled back into the intake manifold. The remaining exhaust gas is mixed with seawater and discharged overboard. Let's look at the advantages and disadvantages of this system. The main advantage of a closed-cycle diesel engine system is that it uses the diesel engine that's already installed on board most submarines, and diesel engines are a very well-developed technology. The disadvantages are limited storage space for the cryogenic fuel, the liquid oxygen. It takes up a lot of room to store. Liquid oxygen storage and usage is also very dangerous, as the Soviets found out with their Quebec-class submarines. Finally, running a diesel engine is just noisy, and that can be a problem when you're trying to be a quiet submarine. So who's using this system? Well, currently there are none deployed around the world. The Germans did install an experimental system on one of their Type 205 class submarines, and it's offered by the German Nordseewerk as an upgrade for existing submarines, but no one's taken advantage of that yet. Next, we'll look at the closed-cycle steam turbine system. So how does this work? Well, essentially it's a conventional steam turbine with the steam being generated from the combustion of ethanol and compressed oxygen, stored at 850 psi. This pressure firing allows the exhaust carbon dioxide to be expelled overboard at any depth without an exhaust compressor. Currently, the only steam turbine system under active development is the French MESMA system. Basically, the MESMA approach is a derivative of the French nuclear propulsion experience, using non-nuclear combustion for the steam generation. The current system has a power output of about 200 kilowatts, increasing submerged endurance by a factor of 3 to 5 at a speed of 4 knots. So what are the advantages and disadvantages of this system? Well, currently it has the highest short-term power output of any of the air-independent propulsion alternatives. Also, the French design does not use cryogenic fuel, the liquid oxygen. The disadvantages of this system are that it has the highest rate of oxygen and fuel consumption of any of the AIP options. Also has the lowest efficiency. Now, who's using it? The primary user is on the French-Spanish cooperative Scorpion-class submarine. Currently, 2 of these submarines are in service with Chile, Malaysia has 1 in service with another on order, and India has ordered 6 of these submarines, but only 3 with the AIP option. The system has also been offered to Pakistan as an upgrade for their French-built submarines. Next, we'll talk about Stirling engines. So how do they work? Stirling engine operates by the compression and expansion of air or some other gas, referred to as the working fluid, at different temperature levels so that there is a net conversion of the heat energy into mechanical work. I'll explain this a little further in a moment, but this picture shows a typical desktop model of a Stirling engine that most of you will have seen as a desktop toy. There are several types of Stirling engines, with the primary kinds being the alpha and beta model. An alpha type uses 2 separate chambers, one for heating and one for cooling, each with a separate piston, while the beta model has a single cylinder where both pistons are on the same shaft. Current submarine propulsion systems use a beta type engine. The beta type avoids some of the technical problems of the alpha type engine, such as some of the hot moving seals that are associated with it. Now we'll see the typical cycle for a beta Stirling engine. This example diagram does not show a combustion chamber or the heat exchangers, only the main sections of the Stirling engine itself. First off, we start out with the general layout of the beta type engine. You can see a power piston, the dark gray piston, in the same cylinder and on the same shaft as the displacer piston, the light gray piston. Both of these are connected to a flywheel. The displacer piston is a loose fit in the cylinder and does not extract any of the power from the working fluid, but only serves to move the working fluid from one place to another in the heating and the cooling sections. In this figure, the power piston is compressed to the working fluid, and the displacer piston is moved up so that the gas is adjacent to the heating section. As your working fluid heats up, it increases in pressure and pushes the power piston to the farthest limit of the power stroke. Now the displacer piston, moved by the flywheel, moves pushing the gas from the heating section into the cooling section of the cylinder. The cool gas is then compressed by flywheel momentum, and the displacer piston moves back up, pushing the gas back to the heating section and starting the process all over again. So what are the advantages and disadvantages of this system? The first advantage is that it's a simple engine mechanism compared to the other AIP engine types. Also, it's relatively quiet, especially compared to something like running a diesel engine. The disadvantages of the Stirling engine are that the engine has to be relatively large compared to its power output. Also, it tends to run at one speed, and so it's very hard to change the power output level. One disadvantage for the current Swedish design systems is that they depend on liquid oxygen as part of their combustion system. So who's using the Stirling engines? The Swedes are the main users. It's deployed on their Gotland class and the Sondermanland class. It has also been refitted to the Västergötland class for Singapore. It's offered by the Kockums company as an upgrade for all their older submarines. It's also being used on the new Japanese Soryu class submarine, and possibly being used by the Chinese on their Type 041 Yuan class. They've reported that they have an AIP capability, but it's not revealed the source, so no one's really sure exactly what they're using. Finally, let's look at fuel cells. So how do they work? In their simplest terms, a fuel cell is a device that combines hydrogen and oxygen to produce electricity, water, and heat. Fuel cells are already seeing a number of promising applications in the space and automotive industries, and many authorities believe that fuel cells offer the best potential for developing a more capable AIP system in the future. For submarine operations, the polymer electric membrane, or PEM fuel cells, have attracted the most attention because of their low operating temperatures and relatively little waste heat. Let's look a little deeper into the fuel cell. The basic components of a fuel cell resemble a normal battery, with an anode, cathode, and hookups to an external electrical load. Pressurized hydrogen gas enters the cell on the anode side, while oxygen enters on the cathode side. A platinum catalyst decomposes the hydrogen gas into hydrogen ions, positively charged, and free electrons. The electrons depart the anode and move into the external circuit, your electrical load, as electrical current. The polymer membrane that separates the anode and cathode prevents the electrons from passing directly through to the cathode, but allows the positively charged hydrogen ions to migrate through the cell toward the negatively charged cathode. On the cathode side, oxygen molecules are disassociated into separate atoms, where they then combine with the hydrogen and electrons to form water. Any excess hydrogen is recycled back into the system. The overall reaction is represented as hydrogen gas plus oxygen gas creates water. And a major advantage of the fuel cell approach is that its major exhaust product is water. A single fuel cell generates only about 0.7 volts DC, and cells are stacked together in series to produce larger and more useful output. The stacks can also be arranged then in parallel to increase the amount of current available. So let's look at the advantages and disadvantages of the fuel cells. The first advantage that we'll look at is that fuel cells have the greatest potential for extending the submerged endurance of submarines. Also, their primary exhaust product is water. The disadvantages of fuel cells right now are that chemical component storage, mainly your hydrogen, can be difficult. Also, they have a low power output for current cells, although this is changing and higher power cells are being developed every year. So who's using fuel cell systems? The Germans are the primary users in their Type 212 and 214 class submarines. Also, they've been offered as an upgrade for the export Type 209 submarine. Another user is possibly the Russians in their Project 677 Lada and 1650 Amur classes. Although it's unclear what type of fuel cells these submarines use, the Russians have said that they have air-independent capability. Now that we've looked at how each AIP system works, let's talk about what they can really do and not do for submarines. Current AIP technology primarily adds low-speed, long-endurance capability to submarines. The AIP systems can double or triple the length of time a submarine can operate without having to snorkel or surface. Current AIP technology is primarily used to recharge batteries, but does not significantly increase the time that a submarine can operate at high speed. The only AIP technology that provided significant speed advantage was the problematic Walter turbine engine. Although it should be noted that because of improved hull and propulsion designs, current diesel-electric submarines can achieve similar speeds to the Walter-powered submarines, and by keeping their batteries in a high charge state using the AIP technology, these submarines can use bursts of high speed. Current AIP power outputs are limited. The maximum power output of current AIP installations is typically on the order of around 400 horsepower. In comparison, a conventional diesel-electric power plant is often rated above 3,000 horsepower, and the typical nuclear propulsion plant produces over 20,000 horsepower. Since the power required to move a submerged body varies with the cube of its velocity, it should be apparent that for at least the near future, the primary value of AIP will be as low-speed, long-endurance adjunct to the underwater performance of conventional submarines. There is little short-term prospect for AIP to become the primary full-performance alternative to either diesel or nuclear power. However, this should not minimize the dangerous potential of AIP submarine. The added tactical flexibility that AIP submarines introduce into undersea warfare make these new boats a dangerous threat to submarines and surface ships accustomed to nuclear or conventionally powered adversaries. The United States Submarine Force needs to understand this threat, where it's been, where it's going, what it means, and how to counter it. Thanks for watching this presentation, and I hope you enjoyed it as much as I enjoyed giving it. If you have any questions, feel free to contact me, Dave Schueler, at the Seattle USSVI base. Thanks again.